Hello to everyone from Maritime Research Institute, Netherlands in Wageningen. I will be presenting the study of global wave repeatability in the Multiphase Wave Lab. To start with myself, my name is Vladimir Novakovic. I work in Maritime Research Institute as project manager. At the same time, I'm also employed at the Delft University of Technology, where I work as a researcher. I'm based in Utrecht in the Netherlands, and my email address is also shown here. To start with why did we do this study? So the driver to perform this study are the sloshing impacts in LNG tanks, which can be found in a variety of vessels. So LNG stands for liquefied natural gas, and natural gas becomes liquid when it's cooled to minus 160 degrees, so that it can be easier to transport or store. Ship motions induce liquid motions inside the tank that can lead to violent impacts on the containment system. What you can see here is an example of sloshing impacts. Today, this method is used for all new designs. The method relies on sloshing model tests to define the statistics of the impact pressures. Sloshing model tests is an experimental model of the reality, so it does not include all the physics and therefore is inherently physically biased. These biases are included or accounted for in the methodology by scaling factors that are tuned based on the long decades of feedback from sea. The reason this is done is because the sloshing impact physics is simply not well understood. And further, the onboard measurements show that long-term statistics drawn by the methodology is conservative, which is good news, but then the short-term statistics is inconsistent with reality, which is bad news. To understand this sloshing impact physics, we must first divide the flow inside the tanks to global flow, which involves the propagation of surface waves towards the walls, and it's considered as the solution of incompressible Euler equations. The local flow is the perturbation of the global flow, and it is directly connected to sloshing impact. The mechanism of sloshing impacts can be divided in three different groups, which are multiphase dynamics, variability of impact loads, and structural response. As mentioned before, sloshing model tests and so the wave impact tests are inherently biased. The basic requirement to obtain wave impacts that are similar at both scales is the similarity of global flow. The global flow is defined by length scale, time and mass scale, and then gas to liquid density ratio. The similarity of the global flow requires that the time scale is square root of a length scale, and the gas to liquid density ratio is should be equal at both scales. Under this condition, the pressures at both scales are related by a unique relation, and therefore the similarity of the global flow is possible to obtain. Now, coming to the local flow, the local flow will perturb the flow similar at both scales. If the properties of the liquid and the gas corresponding to local flow phenomena follow the length, time scale, and the mass scale imposed by the global flow similarity. This requires different fluids at both scales. The right fluids do not exist on this planet for small enough scales. The consequence is that the pressure are not related by a unique relationship given the local flow for practical scales. And now the question is how much each test condition biases the scaling of the impact pressure as imposed by this relation. To answer this and to better understand and account the biases in sloshing assessment method, a research program, SLING, was started in 2015. In this program, we are developing new test facility to perform wave impact tests under very controlled conditions, varying the properties of the liquid and the gas. this facility is under operation, and in fact it was used for the study that I'm presenting. To highlight the capabilities of this facility, we decided to change its name from Multiphase Wave Lab, which you can also see in the paper, to the atmosphere. Now coming to the atmosphere consists of 15.3 meter long and 2.5 meter in diameter autoclave, which can house different setups of up to 8.5 tons. We can independently and precisely control the pressure and temperature. The pressure in range from 5 millibars to 10 bars, and temperature from 5 degrees to 200 degrees. Here on this graph, you can see how precise we can do it. We have the possibility to use different gases, so helium, SF6, nitrogen, and steam, and their mixtures as gases, and then water as liquid to change density ratio, compressibility, and to introduce phase transition. These things are, as I mentioned earlier, really important for the scaling of the impact loads and to better understand and give the input to improve the sloshing methodology. Here you can see the space that we can explore, the space of density ratios and compressibilities, as well as phase transition that we can explore in this facility. Further, we can observe the setups through 17 windows, which are distributed all around the autoclave, and we also use high and low speed cameras for this. It's also important to mention that this is 24/7 operating facility, so we can operate it with little to no human involvement. All right, so coming to the test setup that we used in this study, it consists of 12-meter long flume tank with a piston type wave maker, which is located at one end, and then on the other end we have heavy instrumented impacting wall. We observed the flow using 4 low-speed cameras, which recorded 200 hertz, and the impact is observed with 2 high-speed cameras, which record from 1 to 5 kilohertz. These pictures, you can see this test setup, so the test tank. So in order to assess the global repeatability, we need to generate waves. How do we generate the breaking waves in flume? So a technique widely used is the wave focusing. It takes advantage of wave dispersion to generate a series of waves that interact constructively at a certain point. For example, in this figure that I'm showing, you can see two waves with slightly different frequencies that meet at a specific point. So now that we know that we can create the event that will create breaking wave, how do we move the wave maker to create it actually? For this, we need the amplitude spectrum of the desired wavelet. The amplitude spectrum assigns to each frequency a wave amplitude, and through the dispersion relation, the wave numbers can also be determined, which you can see here. With these wave numbers, we have all the characteristics determined, and we can use linear theory to compute theoretical elevations at the wave maker. So now further to model the wave, to see how the wave will look like, we use Vickers spectrum in this study, as we find it most suitable to model the wave. So further, we included 2 parameters to better model the wave. So we have the parameter beta L to increase the amplitude below the peak frequency, and the parameter beta H that increases or decreases the energy in above peak frequencies. Why is it so important to have a repeatable global flow? The global flow sets the initial conditions for the local flow. The importance comes when we take a look at the pressure maps of the wave impact. Impact loads are highly time-space distributed, and having that the ultimate goal is to observe impact loads, we must create repeatable global flows. Now different authors discuss the challenges encountered to generate repeatable global flows, mainly due to the inability of the wavemaker to mechanically follow the steering signal accurately, or the lack of accuracy in measuring the water depth, and low frequency waves in the flume, also known as seishing or seishing. So how do we know that the global flow is repeatable? So in this study, a method for the quantitative evaluation of the global flow repeatability, we use the method which is based on the Sobolev norm of the Fourier space representation. It's normalized value, so between 0 and 1, when 0 is complete similarity. The expression can be used an intermediate position along the flume where we don't have the effects of the local flow. And then with this, we can quantify the repeatability of global flow. The wavemaker is the most important element in wave generation and wave focusing, because it's far from the impacting wall. Considering the uncertainty in wavemaker motion, a value for the similarity parameter can be theoretically determined at different positions along the flume by simply propagating the control signal that accounts the motion uncertainty to the intermediate position. So as it can be seen, the similarity parameter is independent of the wave crest height and the longitudinal position in the flume. The value Q wavemaker, Q VM, WM of 0.003 can be taken as the maximum disturbance of similarity that can be introduced by the wavemaker to the global flow. And then further, in current study, the total repeatability criterion Qmax is taken to be less or equal to twice the Q wavemaker, and that's 0.006. This means that the global wave shape is considered to be repeatable when the other sources of variability introduce a disturbance of similarly less than or equal to the one produced by the inaccuracy of wavemaker motion. The study showed that seishing in global flow repeatability is not as important as the accurate control and measurement of the water depth. So for typical waiting times, about 20 minutes, which we use in the facility, the effects of seishing are negligible. However, water depth variability has been addressed, and it has a significant influence, and it has been addressed in such a way that we propagate the same control signal at different water depths and then compute the similarity parameter at the intermediate position of 4.8 and 2.3 meters. Solving for water depth that gives a similarity parameter equal to 0.003 results in the accuracy in the wave water depth measurement that is required to obtain repeatable flows. So you can see them in this table. The free surface, the repeatability criterion, presented earlier, of 0.06 was derived with the assumption that the wavemaker performs according to design requirements. To confirm this, we compared the motion of the pedal for different waves with 5-second average error, and you can see that there are large differences in smaller amplitude motions, so lower than 45 degrees. However, the error of the motion between experiments gets much closer to design criteria. In this test, it can be concluded that the variability of the global flow is mainly the consequence of the water depth difference. Considering the wave depth difference between the experiments of delta H of 0.8 millimeters, it is expecting that the similarity parameter Q is larger than Qmax, based on the maximum water depth difference determined theoretically, which I showed on the previous slide. And then the surface elevations at 2.3 meters for experiments, these two experiments, C1206 and C1220, are given in figures. It can be observed that they superimpose accurately with negligible differences in C1220. The resulting high-speed camera images at the moment of impact are shown here. and the superposition of those images indicates an almost perfect match for C1220 and slight difference for C1206. Finally, to come to conclusions, when the analysis of the data obtained from the images showed that when the difference in water depth between experiment was about delta H max, the values of similarity parameters Q were above the maximum similarity value. Then when Q was larger than Q max, relatively large differences are obtained and global flow of the waves is simply non-repeatable. We need more repetitions to confidently state that if we have repeatability criterion less than 0.06, then we can say that we have repeatable or non-repeatable global flows. I would like also to use this opportunity to invite you to online inauguration of the atmosphere on the October 19th, 2020. On this link, you can find more info on this and register for this event. Thank you very much.